Off we go. Okay, so we're going to talk about some fun topics today. This is going to be a set of slides that's chapter 2, and I won't be coding for this one, but I'll be coding for the next one. Okay, so lots of important things to learn about, but I want to start us off with a question. Okay, so this is a legitimate study that happened in real life. If you eat chocolate regularly, you have an 8% lower risk of getting heart disease. That's pretty nice, right? So they legitimately proved that to be true. There was like a group that ate chocolate, a group that didn't eat chocolate. They tracked them over time. They found who had heart disease in terms of like heart attacks and stuff. And so the question is, does that mean we should all eat chocolate every day? I'm not a huge fan of chocolate. Should I start eating chocolate anyway? So I think this is a good thing to discuss. Maybe you've heard this before if you've like taken a stats class, but say hello to each other, get into peer instruction groups real quick, and then convince your neighbor, like, should we be eating chocolate? Do you believe this study? Is there anything that you may not fully accept about it? Yeah.
What was the sample size?
That's a great question. I don't know. I don't remember. We can go look it up. It's in the textbook.
Was there a
But
control group?
I will find those answers for you while you guys discuss with each other. But think about that. That's a great thought.
Like, like that one confined study they did, but these like wonder. No, maybe support.
Sounds like we're not very trusting of the study, and I accept that. But yeah, discuss. What does anything seem fishy, or should we be eating chocolate?
Or the one so what kind of chocolate are they eating? Are they eating like dark chocolate?
That's a good point.
Yeah, what kind of chocolate are they eating? And how much? Saying that eating chocolate makes you healthier is kind of bad. But it was a being precise statement. Yeah.
How long did they stay in for? Like, did they take a bunch of 60-year-olds? Or did they stay in throughout their life?
What brand chocolate are they eating?
Really?
Because
This-
it's like Nestle. You know,
It's a dark chocolate.
Hershey's was just wax.
All right, I think I hear some good thoughts. Let's come back together. Does anybody feel brave enough to share with me the things that you're thinking about? Do we trust this study? Why not? What are some reasons?
The statement's vague.
Well, that could just be me.
You've made it too vague.
Yeah,
There's
that's true.
A lot of different variables.
There's a lot of like what?
Like the type of chocolate they're eating,
Mm.
the brand, is the group randomized, and if so, what kinds of categories of participants do they have? How old are they?
Beautiful.
What regularly?
Yeah.
What counts as regularly? How long do they study them for?
Beautiful.
What type of chocolate?
Yeah. I found a few different studies. This is from the Berkeley slide, so I need to find the study that they were really talking about. But there's a few different studies that some were actually placebo controlled and like legitimately they tried things and they found stuff, but others were like following people over time. So I guess it depends on the study as well. What did you guys think? Any thoughts? Same ideas? It's like it's too many things that we're not sure about. And yeah, at the end of the day, an age-old question, if you've never taken a stats class before, maybe you've heard the word, but like correlation is not causation. Have we heard that phrase before? Like that's where I'm going with this. So like we see that there's an association with this, maybe the study was a good study, maybe it wasn't. But we see an association or a correlation. I think there's only one L in correlation. And then the question is, okay, I see like people who ate chocolate ended up having less heart problems total, but like did the chocolate cause that? Or was it something else? Or was it something else? Yeah, I'll have to find the real study because I found like 3 different studies when I searched for this. I'll have to see which one they were really talking about. But because it doesn't have to be like, let me play devil's advocate here. Like it didn't have to be the chocolate, right? If they followed people over time who some of them like they didn't tell they didn't tell a group of people to specifically eat chocolate. They just followed the people who did eat chocolate. Then that could be a huge problem, right? Because if you eat chocolate regularly, that means you have income that you can spend on chocolate rather than like rent and things like that. So maybe you're more well off. Does that make sense? And then people who have more money tend to like get better health care and like stuff like that. There's like a bunch of confounding factors. Does that make sense? So we have no idea what's going on here, especially if they just follow people who just chose for themselves, right, to eat chocolate or to not, because that could have to do with wealth. And we know that there's definitely gaps in like healthcare quality and things like that among wealthy people and people who cannot afford chocolate to eat every day, right? So that's important to talk about. So yeah, this kind of study was, oh, here, I need to find it. It was this one. It was the people who were in the experiment was a few 100,000, so that's good. So this is the kind of study it was. I'll have to figure out which one it really was. So this was an observational study. This was, we followed people over time. So this study really was following people over time, actually. And they didn't like tell a group of people to eat chocolate and a group of people to not eat chocolate. So that's bad because that's just like the people who could afford chocolate maybe were eating the chocolate. And the people who were involved in the experiment, the word for that is individuals. And it looks like they were in the US, Sweden, and Australia. So let's search for that. Chocolate heart disease study. So we'll find this one now. Dun, dun, dun. Total participants, and it was self-reported rather than randomized controlled. Okay, that's the I'll find a link for that and put it on our slides. I'll keep that tab open. So that's the study, and the thing that we care about tracking for those people over time, we gave them surveys. That's what they did. The thing that they care about is chocolate consumption, and that's actually called the treatment, even though this isn't like a drug trial or something. That's the thing we're studying. So chocolate consumption was the treatment because it's the thing we care about in the study. And then the thing that happened, the thing that we want to see based on the treatment, like what did the treatment cause some change? That's called the outcome. So like what happened to the individuals based on the treatment? That is called the outcome of the experiment, of the study. And we're studying, did they get heart attacks more frequently? Okay, so that's a lot of new terms. So maybe we shouldn't all go out and eat chocolate. It depends. We need a randomized controlled experiment. But yeah, what they found was an association. They found a relationship between the treatment and the outcome. They found actually a negative association, right? Because when chocolate consumption went up, heart disease risk went down. So a positive association would be chocolate consumption going up and then also heart disease risk going up at the same time. So this was a negative one. One went up, the other went down. And yeah, association, another word for that is correlation. So these ideas were correlated. These variables were correlated. Correlation. Cool. So that's what they found. We cannot prove that it was the chocolate causing this. All right. And we'd really like that, though. That's causality. That's when one thing really does cause another thing, like actually eating chocolate really did cause that risk in heart disease going down. But as we were discussing, because it was a self-reported study, people weren't like randomized, put into groups to account for like wealth inequality and like different groups of people handling chocolate differently. There might be other factors, right? There might be other factors at play. So that is unfortunate. Yeah, just like wealth, just like I don't know if it's genetics. Maybe that could also be a thing. So who knows? Something other than chocolate could have caused that risk rate going down. So we're not sure. We don't think that chocolate causes the heart disease risk going down. Okay. So yeah, that's a fun little idea, a fun little thought to get us ready for this, the rest of this chapter. This is chapter 2. So please read chapter 2, by the way. Okay. Are we ready for like the very first controlled experiment ever? The history of this all, like the history of data science. This is the very first data scientist. Let's do some history. So is a man named John Snow was in London back in the day. I think it was 1800s, and people were getting really, really sick. All right, this will be part of chapter 2 when you read it. People were getting really, really sick with cholera, and nobody knew what was going on. Right, there was no like germ theory or anything else back then. But this man, he worked for the government, and he was tasked with trying to like figure out what was happening and try to stop it maybe. So he did a little experiment. He made a map of all the people who were getting sick, and if I scroll or zoom, you can see what was going on. The people didn't have like water delivered to their home back then. You'd have to go out to the little pump of the well, and so there are a bunch of different pumps all over the town. Like, there's a little pump. There's a little pump where people can go get their water. There's a little pump. So he made this little map, and then these little bars that he drew is like the first kind of graph of this kind of things, like epidemiology. He drew a little bar where people died, like where they lived, where they ended up living, and they died of cholera there. And so you see that there's a lot of people getting sick around this particular pump of water. Yeah, because cholera is water related. It's contaminated water. And they didn't know that at the time, but the dude made the map, and he started thinking, right? So yeah, zoomed in some more. It was this Broad Street pump that ended up being the culprit, but some other people in other places were getting sick. And so what is going on here? What is going on here? So he was, so this map is like essential. This is like the very first data scientist. So John Snow, thank you for making this map. And he's trying to study the problem, right? And he sees a association, right? An association of people living close to that pump and like trying to see who got sick, right? And yeah, here's a map. The way that London's water supply worked is, where's the Thames? I think this looks like the river right here. I think this is the river. And there were two competing companies back in the day that were like running the pumps and giving water to people. And I think the Thames flows this way. Correct me if I'm wrong. But there was this Southwark and Vauxhall company that was like supplying water and managing pumps. And then there was this Lambeth company that was also like had some pipes managing pumps and things like that. And the river flows that way. And it turned out that, like, I'll tell you the trick at the end of the day, but let's see. Which was the problem? Yeah, it was Southwark and Vauxhall. They were getting their water downstream. And the Lambeth company, it turns out they were getting their water upstream. And do you know what happens to water as it flows through a city that's a little dirty back in the day? Cholera gets in. So that's what ended up being found. But like that's kind of what happened. And so here's the experiment that John Snow came up with. He had a treatment group. A treatment group were the people who were getting a little sicker than others. It was the Southwark and Vauxhall water drinkers. And then he just kind of grouped people into the other houses that weren't getting the treatment, that were drinking from the other water system. And the place he studied was right here where both of those companies had pumps at the same time. Because like chocolate, we want to study and see if there's a cause, right? We want to see if there's a cause between this pump, people getting water right there, and like people getting cholera. And we need to consider all the other factors, like wealth inequality, like that's a big thing back then too, right? And so the nice thing about there being an area where both water like suppliers were is that we could study and account for the differences in like wealth and things like that, because wealthy people got their water from wherever the closest pump was just as easily as like poorer people. See how that kind of accounts for that? So that's really nice. So that happened. And so there was a treatment group, the people who ended up just like the people who were closest to the Southwark and Vauxhall water pump. The control group was the people not getting the treatment. That was the people who got it from the other water company. And this is what he noticed, and this is how we can prove causation. There was no difference, or there is no difference, whatever, this is his writing, in the houses or the people receiving the supply of the two water companies. There was nothing different other than the water that they chose. Does that make sense? There's nothing, like every other difference in those people was accounted for. Wealth and like average sickness rate and all those things, they're all accounted for where you work. There was no difference in those people. They were all averaged away other than the place that they got their water. Or in any of the physical conditions with which they are surrounded, because like the houses look the same. There's nothing different about those people but the water that they drank. And that, if you can get rid of every other factor, you can prove causality. Does that kind of make sense? That's what he's discovering here. Every other factor goes away. The two groups, the treatment group and the control group, they were similar except for the treatment. And if you can have that, then you can prove causation. Because the only thing different about those people was the treatment, was the water that they drank. And then the differences between the outcomes, right? The outcome is, did you die of cholera in this case? You can prove that it came from the treatment. Does that idea make sense? If you can average away the difference in two groups of people other than the thing you're studying about them, then if there was a difference in those groups, you know that it was the thing you're studying. Yeah? That's what's going on here. And so here's the data that he took as he noticed all these things. You have the Southwark and Vauxhall water drinkers was supplying their water to these many people, this many houses. Get it from one of their pumps. And then we had this many people who died. And then here's the Lambeth company who supplied this water to this many houses, had this many cholera deaths, and then the rest of London had all these amounts. But you can't really see the problem until you do a division, right? You see how if you take, for Southwark and Vauxhall, the houses, and you kind of divide by deaths, then you can get like a rate of how often people were getting cholera. And so this was 315 deaths per 10,000 houses. Compare that with the Lambeth Water Company, 37 deaths per 10,000 houses. So there's nothing different about these people in these two water company drinking people other than the water that they got. And that means that the water was the problem. It turns out that the Southwark and Vauxhall Company, they were getting their water downstream after all the sewage got into the Thames. Okay? And this is kind of like the first controlled study. This is like the first data science experiment. It's very cool. And I hope it makes a little bit of sense. Does it make sense kind of how you can prove that it was the water after all? There's nothing different about these people. They lived in the same area. We could see that there was overlap in the water company, so there really was nothing different. All of those differences in those people were averaged away. The only difference was the water that they drank. And so we can see if there was a higher rate of cholera for the people from one water company, that must have been their water that was the problem. Yeah? That's fun. So that's an exciting thing. You'll read more about that. And you really have to make sure this is true. You cannot prove causation unless this is true, unless your treatment and control groups are similar apart from the treatment. Because otherwise, you'd be like the chocolate where something else could be going wrong, right? Something else could be at play. And so yeah, if there are differences in those groups other than the treatment, then you can't really prove causality because it could have been that other thing. That's very common in those observational studies where you're just following people over time, like the chocolate study. All right. So apparently somebody actually did, when I searched, a chocolate study that was randomized and controlled. So that's pretty cool. We'll talk about those words too. So yeah, that's common in observational studies. And if you conclude something accidentally and it turns out to not have been caused by the thing you're caring and studying about, so that would be called a confounding factor. It's confusing. It's confounding you. And that is when, at the end of the day, correlation does not give you immediately causation. Okay? So when you design your studies, make sure that there's no difference in the groups of people, or the differences have been averaged away, the people that you're studying, other than the thing you're trying to like study, like the water supply, for example. Okay, because when correlation doesn't imply causation, when you have confounding factors, you might be led astray. Like here's some funny examples of that. Maybe you've seen, there's a website that has just a bunch of silly examples of correlation, and it's very clearly not causing other things. So it turns out that over time, how many people eat cheese correlates almost perfectly with the number of people who die by becoming tangled in their bed sheets. Does that mean we should all stop eating cheese to save these people? I don't think so, right? But they're correlated, right? So you can run a study. You can usually find correlation if you look hard enough. But does it mean causation? No, of course not. So that's a funny one. Here's another funny one. Here's a negative correlation. Per capita consumption of margarine, how many people eat fake butter, correlates with the divorce rate in Maine. So should people have stopped eating margarine over time because it used to be like popular in like the 90s. It looks like divorce rates are going down too, so it's heavily correlated. Does this mean we should outlaw margarine to save the Maine marriages? I don't think so, right? There's other things. This is just like, it just happened to be the same, is all. Okay, it just happened to be the same. Not that I'm a fan of margarine anyway, but I hope we can all see, right? You have to account for all the differences in all the groups. Yeah. Otherwise, you get weird stuff like this. So, yeah, kind of the way that you can make things work out is, and make sure that there's no difference between people. You kind of have to have like the same people in both groups so that their differences average away, like I was saying. So an easy way to make that happen nowadays is to randomly assign treatment and control groups. If you do that, if you assign a random group of people to treatment, a random group of people to control, then you will have like averaged away the wealth inequality, the different like groups of people that like think different ways, like all the political differences, I don't know, everything kind of averages away, and you have very similar looking groups if you just take some random people, and then they're likely to be similar apart from your treatment, which means that there will be no bias. No bias when you try to study things. So you want an unbiased study, and you can usually, if there is some slight variability, you can use some fancy math that I won't teach in this class, just kind of like get rid of that. You can control for certain things as well. If you take further statistics classes or data science classes, that's possible too. But usually if you just make a giant random group, it all goes away. And this is called a randomized controlled experiment. That's what we would like to do. All right, if we can make that happen, then we can average away all the differences in the groups of people in the treatment and the control group, other than the thing we have them do, right? We'll have like the treatment group eat the chocolate, the control group not eat the chocolate, and then we can actually study things. And if we find a difference and it's statistically significant, that means we have found something causing something else for real. So that's really nice. All right. And by the way, I'm going to use the word randomness a lot in this class. We love randomness in this class. We're going to use that to like form groups and do simulations to like discover properties of our data sets. And random for us as data scientists or statisticians or programmers, it doesn't mean like the colloquial word for random. Sometimes we use the word random to mean like careless or haphazard or like bad connotation. Random for us just means like perfectly like neutral. We're flipping coins, we're rolling dice, and we're just trying to get things to be like perfectly like a complete random number. That's all we care about. That kind of randomness, not like carelessly random, but like controlled random. Okay, so that's important. And here's a good example, recent, of like a randomized controlled experiment when they were doing the COVID shots, right? So here's like a study that was done by the people who did the Pfizer shots to like, I think they probably had to submit this when they were trying to get like FDA approval to give the shots to everybody. Here is a randomized controlled experiment. There were people who were like, they signed up to be like the first people to try out the Pfizer shot for COVID. And they made two random groups of people, right? And they gave them both shots. Some of them got a placebo, though. There's a control group got the placebo. The real group, they got the real shot. And you can see the the people who got the placebo shots, this is the rate of COVID. It just kept going up because people kept getting it. And this is the rate of COVID among the people who got the real shots and that were in the placebo group. And you see a clear difference, especially after the second one. And there was no difference in the groups, right? Because you can randomize the people, account for any differences like wealth inequality, other stuff like that, where they lived. And this can be used to prove that the shot was working. It was keeping the rate of COVID going down. Yeah. That's really neat. That's really cool. Questions about this? Does it make enough sense? See how to design an experiment? It's like randomly put people in groups, perfectly randomly, flip dice and coins and stuff. And then you can prove causation. So if nothing else, this is chapter 2, and now you can laugh at this comic while I get ready for the next chapter. And this one will have Python in it. Whee! All right, friends. Are we ready for chapter 3 now that we know how to design experiments? Okay, 2 quick chapters. So this one's about Python. This is chapter 3. Please read that one. I'll have to open my Jupyter Lab. Feel free to open up a little temporary link if you want to follow along, or I also made a link for us last night to prepare for today. If you go to the Jupyter Lab page, I have some data sets that we just use in this class, and so I made a second link here that you could click if you'd like that is going to include all the data sets that I'll use in class throughout the semester, so then you can easily import them. So feel free to click that second link if you would like to follow along. There's also ways to you can go to the Code from Class page to get that as well. Whatever you would prefer. But I am going to get started here. I'll make a new file for chapter 3. Whenever it decides to load. But yeah, we're going to use the Python programming language throughout the semester. It's kind of the most popular programming language these days. The other competing language for data science is called R. Maybe we've heard of that one. We've looked into that a little bit. That's kind of just as good, but we prefer Python in this class. Once you learn one, you can it's very easy to learn the other. So I'm going to make a new file for today, and I'll call it chapter 3, so you can have that eventually. And yeah, let's get started. So Python is a programming language, and their mascot really is a snake, but secretly it was designed as a reference to the Monty Python comedy group. So if you've heard of them, there's a lot of references to them in their documentation pages, which is fun. But yeah, we're going to learn the Python language throughout the semester, and so let me teach it to you from scratch now, because I kind of spoke it last time on Monday, and I went a little fast, right? I just wanted to get us all up to speed. So please read chapter 3. There'll be another quick one, but let's do the basics of Python so that we can all be on the same page and it will all make sense. All right. So one thing that we saw, we practiced together was just doing simple math, because technically Python, you can just do math, and that is correct Python. You can say 2 + 2. You can do 4 × 2, and I'm typing Shift Enter to quickly press the plus sign and make a new cell for me. We learned the power computation, so double star is to the power of. It's not the caret operator. And you do have to be careful because you can speak Python incorrectly. Maybe you found that when we were doing it last time. There's unfortunately ways to speak it incorrectly. The stars, they need to be together. You can't say 4 space 2. Then Python gets confused. It thinks that you did 2 multiplications or something. So it'll tell you the problem. Usually it's I put a little arrow. It's that star, I was not expecting that star. That's what it's trying to tell you. And so a lot of the time you can get the idea. So there's that. Yeah, so valid Python is math, and that's the start. When you mess up, you can always look at the error, try to fix it, or ask me a question. Another very important thing in Python is called a comment. And this is you just writing a little sticky note for yourself for later. That if you ever make a line in Python that starts with a number sign, or if you ever type a number sign ever, for the rest of the line, Python doesn't look at that. So you can write a little note for yourself. It's called a comment, and it's not really code. All right, so this is a comment, and it's kind of grayed out a little bit. This is a comment. It's just a note for the programmer. All right, and it's not really code. So if I ran this cell, there's no output. But if I put stuff, 2 plus 2, then it's like it skips it over and it runs the real code, right? It runs the real code. You can even put comments on the same line. You can be like, what does this line do? It adds 2 and 2. And so whenever it sees the number sign, it just like stops looking at the code or whatever you type for the rest of the line. So you can mark up your code with little notes for yourself to remind yourself a week from now what you were really thinking about and trying to do. Okay, but Python will only notice the real code, the stuff that's outside of those comments. Okay, I hope that makes sense. And just shout out if you have any questions about anything. So we've got that. It will be useful for us to save values places, and I was doing that last time. It's called a variable. I want to make a variable, and here's how you do it. You say the name of the variable you'd like to make. Like, let's make a variable called x. Oh wait, let me make it blue. You say the variable's name that you'd like to create, and then you put an equals sign, and then you put on the right hand side of the equals sign what you want to put into the variable's name. And so after this line runs, there will be a variable called x in memory in Python land, and it will hold 42. I like to think of it as like a little box. You can say its name and look inside the box and get the value out. All right. So that's how assignment statements work. This is called an assignment statement. We're assigning 42 to the variable called x. All right. So let me show that to you. So like a good example of like wanting to use a variable would be like pi, right? It'd be like, hey, pi equals 3.1415926527, and then you hit Shift Enter, and now there's no output because I didn't do any math, but it's saved away pi so that I never have to type all that long 3.1415 whatever. I just say pi now. I can say, and I can use it. I can be like pi times, I don't know, what's the pi r squared? So like the area of a circle of radius 5 would be pi times 5 squared. Yeah. That's that. So it's going to, whenever you say its name, it'll look up in the box in memory where it lives, and it'll just like replace it with the thing we put in there. Okay. So there's that. Does that make enough sense? That's an assignment statement that we can make a variable with a name and put stuff in that variable. What else? You can make more variables, of course. You can be like x equals 5. And then you can say x. And it just prints it out whenever you say something. Like the last line of every cell is the thing that gets like converted and output. All right. And I can be like, you can use it in a bigger context. X times 2, because x was 5. It makes it 10. What else do I want to say? I'll do that in a second. Here's something that might make you feel a little uneasy. It's unfortunate that you can do this. X right now, if I ask for it, it's 5, right? I put 5 into x. I can come along and I can say this. I can say, hey, x, now you're 42. That's disgusting, but allowed. Because usually in math, like equals means it never changes, but in Python, it doesn't. It can change however much you want. So this is going to overwrite. Overwrites the value of x. And so you have to always remember, like, what was the last thing I put in there? Because it can change. All right. Now I can make another variable, y equals, 43. And then you can use them both, x plus y. And this will calculate x plus y, 42 plus 43, because x now holds 42. Does that make sense? So I changed it. I changed that box. It used to hold 5, now it holds 42. So now it really does look like this. Okay. What else do I want to say? Just shout out. We're good so far? Questions about any of that? Trying to go as slow as I can. Another fun thing that you can do, because you can reassign stuff, it's a little disgusting, extra disgusting. What do you think this line does?
It adds 1 to the current value of x.
Good. So it'll be what? It'll be 43. Does everybody see that? That's weird, but it will. All right. The reason that'll work, and if I have print x, it will give me 43. The reason that works is the way that assignment works is if you have something, you say like, I don't know, variable equals something that needs to be done first. Like you can't put 2 plus 2 into the variable. You have to create 4. You have to do the math. So the right-hand side of your assignment statements, they're always going to get evaluated, we say first. Python's always going to go right here first to get a final answer and then put the final answer into the variable once it's done. So that process is called evaluation. So this is called a Python expression. It's something that's not quite a value yet because it needs, like, work needs to be done still. 4 is already a value, we say, but 2 plus 2 is just, they call it an expression because it's not a final value. It needs to be evaluated. All right, so we need to evaluate it. Python will do it for us to create 4, and then it puts the final answer into the variable. So the right-hand side of every assignment statement happens first, and that's why this makes sense. All right, because it's going to run the right-hand side, RHS, first. RHS gets evaluated first, and then put into the variable that you put on the left-hand side of the assignment. So this will calculate when x was 42. If I run it again now, it'll be 44, right? But if I ran it before, when x was 42, x plus 1 happens first, so that'll be 42 plus 1, 43, and then it shoves the 43 into x. Yeah? So that's why that's happening there. Okay? And so I think that is what I want to say about all of that. A little weird that you can redefine variables. Well, we get used to it. Okay? So the equality is not like the math equality. It's called assignment. We're putting a value into a variable. It would have been nice if this was like an arrow or something, because that would make a lot more sense. Like you're shoving a value somewhere. But nope, we're going to use the equal sign for all of that. Any questions so far? Just shout them out. And so when you have variables and this kind of idea of like evaluation before assignment, then you could do some cool stuff. You can calculate, like, I don't know, you can write code that you can come back to later and it will make sense to you. So like say you're writing code for like a checkout stand at like In-N-Out or something. So you can be like the subtotals value, we calculate it to be $9.99, and then the tax for this is going to be the, I don't know, it's going to be the subtotal times, I think it's 8, I don't know, let's do like 8.75% tax for wherever we live, and then the final total is the subtotal plus the tax, and like you just round that, and that's what you tell the person at the checkout stand to pay to you. And you see how you can come back to this code later and understand exactly what you were talking about? That's the beauty of variables and like spelling things out like this. Yeah, I think that's what I wanted to say for that slide. We good still? Yeah, not horrible. So this is very quick. Like I like to come to Python and just do like math every week when I pay my credit card. Like I just do a bunch of pluses in Python and I figure out, all right, what do I need to pay right now? So, okay, the next thing I want to talk about is called function calls. Another word for that in Python, like the generic term is called a function call. That's like across languages. Python calls them call expressions. Doesn't really matter. I'll call them function calls in this class, but a function is pre-written code. I'll eventually teach you to write your own, but a function is some piece of code that somebody has written before, maybe you, that has the ability to do something. So the way that it works is somebody's made, or you have made, a function with a name, and you can call out to it, like the metaphor is you're shouting out it, like, hey, do this thing for me function. And the way you call it is you say its name, and then you put parentheses around the things that it needs to do its work. And we call those, to keep the metaphor going, we call those arguments. So you're calling to the function, you're arguing with it, you're giving it the things it needs to do its work, and then it will result. It'll go off and call the code that was been pre-made for you and give you back an answer. All right, so for example, here's like if there was a function called f, and it took one thing to do its work, you would give that between the parentheses, and then you say it like this, all right? So yeah, these are called arguments to the function. When you call it, you're asking it to do work, and you're giving it the things that it needs to do its work on. Arguments. So this is like you shouting to f, hey f, do the thing you were meant to do with the number 42, because you need that one thing to do your work with, all right? And so a good example of like a built-in function in Python is the maximum function. The maximum function takes at least one thing, usually at least two, but it would work with one. Just give you back that thing though. But it takes, and you comma separate your arguments. You can give it, you can ask, hey, what is the max of 2 and 3, right? And so this will result in what? If this code runs, what should it give back? It should just give back 3, yeah? Good. So it results in the answer. We're calling max, this line, what it's saying is we're calling off to max with 2 and 3 as the arguments. Those are the things we want to ask, which is the max. Like, I want the max of 2 and 3, please, Python. And it results in, it'll turn into the final answer. It'll do the work. Go off to wherever the code was, the nice people that made the max function for us, and it will find the bigger thing, give that bigger thing back to us. It results in that answer. A word for resulting in that we'll care about later is called returning. It's returning back to us. We're calling it, it's returning. It's responding to us with the answer. Okay, so let me show that to you. I'll make a new little section. Function calls. By the way, if you change your cell from code to markdown, it can be pretty text. So that's what markdown is. So this is called markdown. It's like a programming language for making like pretty text and documents. So it's a programming language to make pretty documents, which is nice. And the number sign in that, in markdown land, means heading. So this is the level 1 heading. But that's beside the point. So okay, yeah, max. Max 2 and 3 results in 3. Goes off to the code, somebody who made the max function for us. We're calling off to it, giving it 2 and 3, and it will give us back the 3, the bigger thing. All right. Another good function is the round function, because like this, you can't pay in thousandths of a cent, right? So you really want to turn this into 1086, really. So the way you can do that is you take the thing you wanted and you give it to there's a function called round, right? There's a function called round. By default, it'll round to the nearest whole number, so it's like 11. But you can also give it a second argument optionally to say how many decimals to round to. And so if I run this one, that'll turn it into 1086 from this original addition answer. Does that make sense? So sometimes the function works a little bit differently depending on how many things you give it. Sometimes it needs really always 2 things, but some functions are okay with fewer or more. Like max can take 100 arguments. If you give it, it'll just find the biggest thing of all of them. So some of them work with a bunch of things. Some of them like need one and only one thing. For example, there's an absolute value function. It's called abs. And if you give it, you can only give it one thing, the thing you want the absolute value of, right? You can't forget. You can't give it 2 things. So that'll give you back the positive version of whatever you give it. Okay, so that's function calls. Just to make sure we kind of understand what's happening, here's like a bigger chain of function calls. Try to run this code in your head and convince your neighbors that you're right. Try to find out this answer and see what it should be. What should this result in? But try it in your head first or on paper. Even. Take a few seconds. Or try that.
Oh, is it?
Can I see what it's trying to do? You can ask me a question if you like.
Yeah. Yeah. Parentheses. For this, it means the text.
Any brave soul have an answer? Have an idea? Do we agree? Yeah. You agree that it's 48? You guys think it's 48 too? 48? Something different? Okay. Well, do you see how we're kind of parsing this? It's like this big long thing. If you follow the parentheses, like this is all together, right? And then plus 42 to whatever that is. So in order to take the max of these things, you kind of see what Python must do. It has to evaluate the inner stuff first. Yeah, it has to do that. Otherwise, it doesn't know what to take the max of. So the inner stuff happens first. So it will try to find this answer, and this answer, and then take the max of those 3 things. Yeah. So the min of all those is 1. The max of 4 and 5 is 5. The min of 6 and 7 is 6. And then we take the max of all those things. So this, the way Python does it is like, it does all those inner things, and kind of the line itself turns into now max on 156 plus 42. That's how it's like simplifying to get its final answer. That's what Python's thinking about. Okay? And then now, like, it knows what 42 is, it knows how to add, it just doesn't know this answer yet, so it has to go figure that out. That's going to go call max, and that will result in 6. And then it'll add 6 and 42, and like that, the line turns into that now. Python is almost done. It needs to evaluate that finally to 48. And so that will be the answer. Yeah? I don't know if that makes enough sense. So do you see, like, Python is going to do it in the logical way. It's going to do it in the way you think about it. So there's that one. What else? What else? Let's do, yeah, the next thing I want to talk about is these are all built-in functions, the ones that I just showed you. They're just like baked into Python itself. There's a bunch of other places that functions live that you might want, but they're not going to just like be baked in. You have to ask for them to be part of your program. That's called a library. You check out code from the library. All right. So a library is just a bunch of pre-written code, a lot of functions, for example, that you can check out and use. A good one to learn first is there's a math library in Python that has a bunch of math functions. So like sine, cosine, and tangent, they're in Python, but they're not there right now. So like sine of pi, it doesn't work yet. I have to include it. All right, I have to include the library to ask for those things. And then it'll work. Oh no, so there are some libraries that are baked into Python that you can ask for. They're there already, but you just have to ask to include them in your current program. But there's other libraries that you do have to download, like the ones for this class, the data science library. That's one of the ones that were like in that first setup file. That was downloading that for us to use forever. Yeah, the math library is built into Python, but it's not in your program until you check it out. So let me show you what's in the math library. The sine function's for sure there. But you can search for Python math. And there's documentation on each library that's in the Python language. And so here's the math library, and it's got all these things in it. You just keep scrolling, see the cool stuff that's there. You better believe that there's sine, cosine, and tangent eventually, but like there's logarithms, there's e to the something, exp is what it's called. There's the square root function. There's a different version of power. They call it pow, the first thing to the power of the second thing. Converting from degrees to radians. Inverse, cosine, sine, and tangent. There's normal, sine, cosine, tangent. Yeah, there's a bunch of ones. And there's also variables inside the library. So there's a variable called pi define. It's probably where it belongs, right? It belongs in the math library. There's a pi, there's an e. And those aren't functions. Those are just variables that are part of the library that you can ask for. You can check those out too. So the way you include a library in Python is you import it into your code, right? So we have to import it first. So we have to import the math library to use its stuff. And so that's why there's an error right now. Python knows that there's a math library, but we haven't asked to use it yet. We haven't checked out that book. So to get that, you say import. You say import math, import the name of the library. And then once you've done that, now all the math functions and variables are available to our program. But we do have to qualify them just in case, and the reason Python does this by default is just in case you want to make your own version of the pi variable, like we did, just in case you want to make your own version of the sine function. They don't put it by default. They don't just call it sine. You have to use the name of the library. It's like inside of the name of the library. So to get at like the square root function, you don't just say square root. By default, it's not just square root, even though that is the name of the library. You have to qualify it with the name of the library. So it's not just square root of x. You say math dot square root of x. It's part of the math library, and that's where it lived, and that's how you call it. So that's where its name lives. And so that also makes it so that you can use two different math libraries, and there won't be any confusion. Like import math2 if you make your own math library, call it math2, then you have your own a separate square root function that you can call. You can see if that one's more efficient or something. So yeah, that's the math library. There's, of course, you can do sine, so math.sine, use the math version pi, sine of pi. This is very, very small. It's supposed to be 0, but it's kind of imprecise. We can round that answer to the nearest 5 decimal places, 0. So that's a fun idea. You can always go to the documentation page and click on them to figure out like what this does. Square root's very easy, but some other ones are weirder. like, I don't know, there's a logarithm function. Where was that? There it is. And like this one takes one thing and then optionally the base, by default, it takes the logarithm base e, the natural logarithm, but you can also give a base. So if you don't want to go to the documentation, that's all built into Jupyter actually. You can say, I'm thinking about calling math.log, but I don't really remember how to call it. I want to know more information about it. You can say question mark, say math.log question mark, and then it will give you back the documentation for that particular function, which is really cool. And so everything we found there, it's going to give it right back to us. So like, okay, yeah, I want to call it like this, math.log. Let's do 32, logarithm, log base 2 of 32. That's 5. 2, 4, 6, 2, 4, 8, 16, 32. Yeah, cool. So there's that one. If you don't want to say math.square root all the time, if that's a lot of typing, you don't want that. You just want to be able to say square root. The way you can say that is you can say, instead of import math, you can say from math, import square root, and that imports it as like the top level we say. So then you can just say square root. Like I want the square root out of the math library and I just want to be able to call it square root. Then you can get at those things that way. Import them into the top level so you don't have to qualify them with math dot all over the place. Okay, so that's one library. There's plenty more where that came from, but that's a useful one. Are there any questions about that? Pretty self-explanatory, right? Very useful. Important libraries that we're going to care about is the data science library. So there's a data science library that is made just for this class that is very similar to the things that, like all the functions that the real data scientists use. It's just made to be a little bit easier for a first-time student. One of the functions that we care a whole lot about for us, this class, for this semester, is in the data science library, there's a function called table that will build a table for us. That's perfect, all right? So a table is just a bunch of columns with labels. And so here's what a table looks like for us in our data science library that I'm about to import. So here's a big long table. It's got 3 columns, name and code and area, parentheses, meter squared. And every column has a label and they have values. And then the opposite of a column is a row. So here's information about one particular state. That's a row, and it has the name part, the code part, and the area part. It took me until I was like a junior in college to figure out the difference between row and column. But think of it this way, like you got the Parthenon, right? These are columns, right? They're going this way, up and down. It's like the boop, boop. Those are your columns. And then rows, I guess, I don't know, kind of looks like a canoe. That's the difference. So rows are the horizontal thing, columns are the vertical thing. Okay. But yeah, let's make some tables. I want to do that for us. Do I want to do that right now? Yes. Yes, I do. So I would like to include the data science library. And I don't want to say data science dot all day long because we're going to use so many things in it. I don't want to say data science dot table. I just want to say table. So I'm going to do it this way. I'm going to say from data science, like import table and all that. But I'll say just import everything because we're going to need them all. So here, let's do tables. So I'll say from data science. So we installed this particular library ourselves. This wasn't baked into the Python language, but we downloaded it. I say from data science, import everything. Please and thank you. So that star, as I was working on that, the star imports everything into the top level, like I've been saying, so that you don't have to qualify it with a data science dot. So I don't have to say data science dot blah, blah, blah all day long. That's very nice. Okay, so that is the data science library. And then there's the idea of a table inside of that. I can just say table. And one easy way to get a table is to read it from a file. So there's a function on tables called table.read_table. And you better believe we can put a question mark and learn more about it. So here's a function. It's called table.readTable. And you give it only needs one real thing. You give it the name of the file that holds the table you want to read and create one out of. You can also give it a URL, which is fun. But that's how you use it. You say table.readTable, you give it the name of a file, and that will get stuff for you. Okay? So I have some files in my data folder here, a bunch of them. I'm going to import one easy one. I'm going to import one easy one. It's called cones.csv. It's like a bunch of ice cream cones. We're going to pretend we run an ice cream cone stand. And here's a CSV file that we're going to import as a table. All right. So there's 7 rows. There's 3 columns, flavor, color, and price. And so there's a bunch of flavors. And so like each row corresponds to one ice cream cone that we sell at our store. All right. So strawberry, pink, $3.55, chocolate. There's 2 different kinds of chocolate. And so there's the prices of our ice cream cones. And so I'd like to take this CSV file, it's short for comma separated values, and I'd like to import that as a table so that I can have it and do Python with it. So the way that I can do that is I can say table.read_table, and it's always relative to where I am. So I'm here in this chapter 3 file. It's inside the data folder, and you give it between quotes. It's inside the data folder, and it's called cones.csv. And if I hit enter, it turned it into a Python table, into a data science table. That's really nice. And if you are following along, there's a couple different ways to get that file right now. If you click this second link, you can do exactly what I did because I included that file in the second link with all our data sets. If you'd rather not do it that way, you can go to our code from class if you haven't been there yet. And then there is a data folder there. So you can click data 8, it's a bit harder. You click our data folder, and then here's the cones.csv file. And you can download it. There's a little download button right over there. And then you can drag it into your version of Jupyter if you'd like. But it'll always need to be, like, if you drag it into the same folder, then it's not like data slash. It's just like, if you put it in this current folder, you just call it cones or something. Okay? So I can help you with that if you'd like. But yeah, here's the table, and let's call it something. Call it cones, so that I can use it and have it around. Because otherwise, without a name, it just kind of goes away. So now I've called this table cones, and I can do stuff to it. All right? Are there any questions about that so far? So I've just made a Python. I've turned this file, I've read it, into a table, which is like this kind of way of talking about the data, all the rows and all the columns with their labels. And then I can eventually like do stuff to this table. Like, give me the cheapest cone. Like we can ask questions about the data. Eventually we'll be getting to that. Okay? Are you ready for that? Okay. So yeah, to learn more about the data science library, I've got a bunch of those references pages on our Jupyter Lab page. So we've got Python reference 1 and reference 2, whichever one seems more interesting to you, you click on. I think I had them here from before. So here's reference 1, reference 2, whichever one you would prefer. So here's a bunch of things you can do to tables. Here's table.readTable over here. You can like learn more about it and all the other operations that you can do. You can make a table and add columns to it. You can get, I don't know, you can sort parts of your tables, and you can learn more about it by going to this documentation page. So there's one here, and there's another here, whichever one you would prefer. This one's a bit more shorthandy. It's like table.readTable, blah, blah, blah. So yeah, whichever one you would prefer, these will both have the right answers in them. But this one's like more shorthand. This one's like more longer examples, whatever you'd prefer. But we got those 2 pages, and here's some important operations on tables that we care about. All right. I think the first thing that I want to show you is not actually on here. There's, if you just want to see a little bit of your table, you can say .show. There's a show operation on tables. So where's that? So if you have a table, you can say .show on it like this. You say its name, .show. So you're asking the table to show itself. It's a weird kind of function call. It's built into the table. So you can say show and then give it a number, and it shows that many rows of the table. But if you don't give it a number, it shows you all the rows. So here's my cones table. I've called it cones. Like I read it, and I put it into this variable. And I can say cones.show the first 2 rows. And so you say show 2. It gives you the first 2 rows. And it omits the rest. If you have a big, long table, by default, it only shows you the first 10 rows. We read into that last time. If you want to see everything, you just say .show without anything at all. And it will, by default, show you every single row in the file. But this one was small enough for just like to print out its name. It showed you everything anyway. But show will give you the first few rows, or all of them. And Yeah, then the first real function I want to teach you on tables is called select. So if you have a table, let's pretend our table is called T. If you say dot select and you give it names of columns, it will make you a new table based on the old one called T, whichever its name was. Ours is called cones right now. It'll make a new table with just those columns. So you can like get rid of stuff or rearrange stuff. All right. So for example, I can say cones.select, and I can, these are the labels of my columns, flavor, color, and price. They're all capitals. I can say dot select flavor, and what this will do when I run it, when I shift enter that, it will make a new table based on just this first column. It'll give just that first column back to me. Does that make sense? I'm selecting out just that column, okay? And this gives me a new table that I can then put in another variable name and work on. That is something you can do, and it does not change the original table. All right, it makes a new table just with those columns in a different order potentially. And the old table, so if I ask for cones by itself again, it has not changed. It's still there. I've not gotten rid of anything. This makes a new table always. So that's good. This one hasn't changed. Okay, so that's nice. You can select multiple things, of course, and be like cones.select. Give me just flavor and color. Or let me do it backwards real quick. You can do color then flavor, and then whatever you say goes. So this will give me a table with color first, then flavor second. That's nice. Or I can do it the original way, flavor then color. Whenever you want to give the name of something, you use quotes. You can either use double quotes or single quotes, but I prefer not to press shift. Python doesn't care as long as you're consistent. So I could have said double quotes color here and it would have been happy. As long as you're consistent, it's fine. Yeah, so there's that one, that's select. And yeah, you can read more about it on either of these pages. So table.select, you just give it whatever columns you want to select out, and it has some examples, and you can see how you can kind of chain operations. That's what that page shows. This one also says select. It's just a bit more short, and like maybe this is the file you look at like on an exam, for example. So, by the way, when you guys take tests in this class, I'll let you use both of these pages while you're taking the test. Just no other pages. But you don't have to like remember these names. You can use these two documentation pages. So it's good to get used to them now. Let's see. Yeah, so that's select. Just shout out if you have questions. Drop is the opposite of select. Drop takes a table and it gets rid of certain columns. It gives you back a new table with every column that you didn't mention there. All right. It omits the columns with those labels that you give it. So we can say, let's say cones dot. Another way to make this exact table would be to start with the cones table and drop just the price column, right? Drop just the price column. So that's another way to do it. So take the whole cones table and drop the price. And that's another way to make this exact same version of that table. Yeah. And it's always a copy. You never have changed anything. So you can like use that copy if you save it away. So you can say like, this is cones with no price. Call it that. That's nice. And yeah, again, the original cones table has not changed. The original table is still there. Everybody's happy. But there's a couple ways to get at things. You can select out the columns you want or drop the columns you don't want. Okay, there's that one. There's sorting. You can say table.sort, and you can sort by a column that you care about. Usually it's a numeric column, and it will sort all the rows based on the column that you're asking to sort by. So we can say cones.sort by the price column, and this will rearrange the rows. I'll keep them next to each other. This is one thing that's always going to be a chunk together that's going to put that first, right? And so that was the cheapest cone. It's going to sort ascending by default. But if you look at the documentation, somewhere, I always have to look on the left side and see what, you can say there's an optional thing that you can give it. You can say descending equals true. So this is like a variable argument. It's a weird thing. I think you could just say comma true, but this is called a named argument. And so the way that you can run it is you can say sort by this column name, descending equals true. And true just means yes in Python. So default, it's descending false. False is no in Python. So I can say sort by the price. This is ascending. If I want it the other way, I can say descending equals true. And this will sort by price descending. Rearranging the rows in that way. Okay. That's a weird kind of thing. Are we ready for the coolest, arguably, operation on tables? The one with the most power. Is called .where. And then this one, I'll just start us off with the easiest condition, but this one is very powerful. It's this .where gives you back rows that match a condition. So you can say, give me all the rows in this table T where this condition is true about this column labeled this. So this is very, very powerful. You can say like, hey, give me all the rows in the table T where the price, and then there's a way to ask for like, is less than $5. That's very useful. Yeah. So that'll be fun. So it gives you back a new table, and this one will give you back just the rows that match that condition on that label. Okay. So technically, all of these first operations were column based. They're messing with columns, bringing them in, putting them away, sorting based on them. The .where is kind of row based. It's selecting out rows only. So it's kind of the other axis of all these operations. And so that's kind of cool. So look at the documentation for that. It's a little weird to do a .where and ask for what you want. You have to use, I don't really agree with the way they did it. They're trying to make it easy on you, which is still confusing in my mind. But like if they had a cookies table, you'd say cookies where the amount remaining column values are above 10. That's how you think about it. You have to say r dot something. It's a little weird. R equal to chocolate chip, where the values by default it's equal to, where the price values are below $1.25, stuff like that. So I'll teach you more of that soon, but that's a good start. Okay. By default, when you do a .where, it's going to ask for equality. It's going to do an equality check. So if I have my cones table, I can ask for all of the chocolate cones by saying cones.where the flavor column values are chocolate. By default, it's going to give you equality checking. The condition is equality checking. So where the flavor column values are exactly equal to chocolate, it'll pick out just those columns if I run this right now. Does that make sense? So go on the side of the cones table, here's the whole thing. Where the flavor column values are equal to chocolate, only give me those rows. See how it's asking that? That's very powerful and useful, even for just equality. But you can do more. You can be like, where the price is between $4 and $5. Like, you can get real fancy with it. It's very nice. Okay? So I think I just want us to play around with that. Let me show you a fun one. I've got a bunch of tables, like example data sets in this data folder. One is like a list of all the Pokemon, because I grew up and I was a very big fan of Pokemon as a child. So I've got this Pokemon.csv file with every single Pokemon up to Gen whatever last year. And it's got all these different rows and columns and a bunch of different information about all the different Pokemon in the Pokemon universe. So let me import that table for us. And I'd like you to follow along. If you go to the file that I gave us on here, I've already got it including the Pokemon file for you. So if you go to that link and you run all those cells. But I'm going to read the table because I'm out here. I'm in this chapter 3 file. I'll say table, read table. It's in my data folder relative to me, and it's called Pokemon.csv. You can usually type a tab, and it'll fill it in for you with the file name. And then I want to call this something, so I'll call it Pokemon. And then I'll do Shift-Enter, and here is my Pokemon table. It only shows me the first 10 rows by default. And it's not in any normal order. It's in alphabetical order by column, so like abilities is the first thing. That's not very useful. But here's a bunch of things about each Pokemon. Each row is a particular Pokemon. Their names are over here. Here's their name. So in order of Pokédex number, Bulbasaur, Ivysaur, Venusaur, and like Pikachu's down here eventually. But you've got all this data on all these Pokemon. You got their speed, you got their types. Their primary type of Bulbasaur is grass. The primary type of Charmander is fire. There's a secondary type sometimes, like Bulbasaur's secondary type is a poison type. The word Nan will come up eventually in data sets. I might as well talk about it now. What Nan means is there was no value. Nan is short for not a number, which is kind of useless because this is supposed to be words, but that's okay. Nan just means there wasn't a value. Not a number, not anything else either. This is the generation the Pokemon was from. Is legendary, is 0 if it's a non-legendary Pokemon, and 1 if it was a legendary Pokemon. The height, average height of the Pokemon, the HP at level 50 of the Pokemon, their defense values, their capture rate, all these values that you care about if you're playing the Pokemon game. How well do they interact against electric type Pokemon, stuff like that. So this is my Pokemon table, and I just want us to explore it. All right, so I'll say I've read it in here with this table.read table, put it into a variable, and I can ask, like I can find Pikachu, I can be like Pokemon.where the name column, right, because it was called name lowercase way over here, where the name column values are equal to Pikachu. And every time you have a word, you put it between quotes. And then here's the Pikachu row, because there's only one called Pikachu. It's like mass Pokemon defense. HP at level 50, or some level, is very small apparently. And very, very quick. Primary type is electric. Doesn't weigh very much. Generation 1 Pokemon. But like, there he is. Or she. So, it was perfect. And you can ask for, like, I don't know, give me all the Pokemon that are electric as their primary type. So where their type 1 column values are equal to electric, I can be like Pokemon.where, and I encourage you to play around while I'm playing around. Type 1 values are equal to electric. You can start sorting by speed and attack and all that fun stuff. Find the fastest Pokemon, find the strongest Pokemon. But it looks like here's all the electric Pokemon. Here's their names. Pikachu is the first in the order. And here's all the other electric Pokemons as their primary types. That's pretty fun. And so, yeah, I just want to show you a couple ones, and I'll give you one answer, but try to play around as I'm playing around. So, I have a soft spot in my heart for the Generation 1 Pokemon. So I can ask for Pokemon.where the generation column values are equal to the number 1. And the number 1 is just a real number. It's like, it doesn't have to go between quotes. So Generation 1 is a Pokemon generation. That's just a number. It's not a word. And here's every Generation 1 Pokemon, all 151 of them. So, and I can call that something, because every time I say .where, every time I say .anything, it gives me a new table to work with. It's not changing the old one. So I can say, like, Gen 1 equals all this, and I can work with that table now. Okay? So I can find, like, the strongest Gen 1 Pokemon now, because I've got this Gen 1 table. I can take that and find, like, the attack column. Right? Where's that? Strongest in terms of how badly it can attack things. So a bigger attack number means it can attack better, I guess. So there's the attack value. So I can say Gen 1 dot sort by attack, right? And then by default, it is ascending, and that's not what I want, right? I would like it to be descending. So here's like the worst Pokemon ever in the first generation with attack of 5 is Chansey. I'm so sorry, Chansey. And then you can say descending equals true to get it in the other order. Capital true. Oops, I put too many parentheses. And so here are the strongest Pokemon. The first one is the strongest. 155. So these are two together, I guess, is the strongest in terms of attack. What are they? Pinsir and Gyarados. Cool. I can't show both of them at the same time, but here's like the strongest Pokemon in terms of their attack values. So I sorted by attack, descending. Do these ideas make sense? Even if you've never seen Pokemon before. Hopefully you can kind of get it, right? The last thing I want to say before I give you one example to try and ask you to do it and like import it, make sure we can all do it together, is you can chain these operations. That's really powerful. All right, because once you do this, once you ask for something, it's giving you back a new table, and that entire thing kind of turns into the table, whatever you say there. You can imagine this entire expression turns into the table itself that you can use, and then you can ask something of that table. Because like you can say like this whole thing, right? I put them in parentheses. You don't really have to do that. Like this whole thing turns into a table, and tables you can say dot select and dot sort and dot other things on, right? So like this whole thing is a table. It will result in one. So I can be like, you know what? With that resulting table, select out just like the name, the primary type, and the attack values. Give me them in that order. Does that make sense? I can chain these ideas. Because like this first one gives me a table. Then I can ask for more stuff about that particular table that I got back. I can chain one after the other. Sort, then select. Does that make sense? Because it's giving me back those things. It's working in that way. And you don't need these parentheses. Python doesn't care. And so it's like this whole thing results in the table that has attack values descending. And then you can select out just the columns you care about displaying. And this is much easier to look at, right? You don't have to scroll over. And this is me chaining those thoughts. Yeah? That's pretty cool. That's easier to look at. That's what I wanted to see. And then you can like show, you can be like, dot show a few of them, more than 10, for example. You show them all. But now I have a question for you. So please include the Pokemon table here. You should be able to, the easiest way to do it is just to go to this file, this temporary link. It's already going to give the Pokemon table into your Pokemon variable. I can help you otherwise if you'd like to do it in a different way. But here's my question for you guys to try. You guys can help each other once you find the answer. Try to find the top 8, only the top 8, Generation 2, so not Generation 1 anymore. Find the top 8 Generation 2 Pokemon with the highest defense values rather than attack values. So the ones that can take the most damage. But they were from Generation 2. I want to just see the top 8 of them. Does that question make sense? You have an idea of the chain of things you would do to get there? So as you're thinking about that, I'll keep this one up. That's kind of this similar idea. What else can I do for you? I can give you this file that we've worked on today so far as well. So let me do that really quick. I'll give you a few minutes to play around with this, and then you can ask some questions. And then we'll wrap up after that. So let me go to the code from class real quick. And so if you go to our code from class, so you can go, it's right here, our code from class, and then you click on data eat. What I've done is I've given us everything I did today in this chapter 3 file. So if you click on the chapter 3 file, you see everything we did with our tables and everything else above that too. You can just scroll. Every single thing we did is here. So including all those .where things and all that fun stuff, so you can remember how I did all that, because I can't scroll and show you everything at once. But now you can scroll and see it all. But get that Pokemon table. Try to find the top 8 Gen 2 Pokemon with the highest defense values. All right? And let me know if you have questions as you're trying. I'll give us a few minutes. And help each other, please.
Having trouble getting that table as well.
It's good to get this second nature, because then you can start asking questions in any case. Similar way.
Get that one. Some more. So if you're stumped, I think your first steps are going to be either think about Gen 2 Pokemon or think about highest defense. Yeah? One of the two, you should start with one of the two of those. But the order of those two doesn't really matter. I think getting the top 8 has to happen last. Yeah. And if you're having any trouble, ask me. Yeah. Oh, okay, good. Let's. Did you run those cells to include the table? Nice. So you got it. And let's see. So, what if you're doing this on paper? Like you're just looking at the table and trying to like cross out lines and cut out lines. Like what would you do? I think I'd go looking for the Generation 2 Pokemon first. Yeah. Oh, okay. So can you let me scroll up. That's just a row. Sorry if you've never experienced Pokemon before. A generation is just like there was the first set of Pokemon video games. That was Generation 1. They had a bunch of magical monsters then, and then they made 100 more for Generation 2, and so the generation column, like there will be Pokemon with generation set to 2. That's where we're looking. So this is how I extracted the Generation 1 Pokemon. I did a where on generation and set it to 1. So you'll do it with 2. So you'll do something very similar to this, but ask for the Generation 2 Pokemon. So here, let me paste this down here so you can have that. Well, everybody can see this thing still. That was getting us Gen 1. You see how you change that to get the Generation 2 Pokemon? That way to generation values. Nice. And so that gives you a thing called Gen 2. Now you can say Gen 2 dot stuff. Does that make sense? So now, from out of the Generation 2 Pokemon, let's go get their highest defense. Maybe that. What would that involve? This is like how they attack. You got plenty of time, and if you're running the errors, do you understand what it's asking? What it's telling you? Oh, you have to say descending only. There isn't an ascending. Ascending is the default.
Still looking at the up.
So either you say nothing and it's ascending, or you say descending equals true and then it's happening. So yeah, you can omit that if you want it to be ascending.
Nice to meet you.
Now it's sorting ascending on defense. Okay.
So,
I'm gonna get some more water.
That'd be right.
Yeah.
can you specify by generation?
Oh, wait, I know one. This is important.
Next, yes.
Celebrity. So you have highest. Just shit that right.
Is it what should be?
Now. Oh, no, just straight down. Oh. There you go. That's fine. I had the same issue.
Yeah, I was like,
What are you guys doing? Yeah, just do show them.
yeah, nice. Secret.
Don't say you know what game that is.
What shows are
Don't show.
Okay. What's that? Oh, that just turns it into, because like, you scroll up a little bit, you remember how it had a million things, it's showing you all these things? Select out just the columns you cared about. So you don't have to do that if you don't want to, but it made the output easier to look at. That's why I did select. Just give me the 3 columns that make sense to me.
So first I started by sorting by defense, and then I tried to sort it where based on defense it was only Gen 2.
Nice. I looked at you guys are helping each other. Swarms and hearts. Yeah, if there's something you can't figure out, please yell at me. You guys have that yet?
So this is all by defense.
I got some miles out. Do you understand what it's asking? They fun? Just, okay, yeah, so we got the Pokemon table, we got the generation 1 right now, but we do want generation 2, you know that, yeah? Right, now you're looking at generation 1. Oh, sure, yeah, so sort, you got it. Maybe you need to call them. It's not a type column, it's a type 1. There's a type 1 and a type 2. Weirdly enough, there's no column called type. So that'll work. But yeah, actually, by typing Pokemon, you didn't actually see the last thing. See the first. Yeah, that was always the last thing in your cell. So bring it back out to you.
You don't have it as a number that's incomputable, but.
So now make it Gen 2 defense.
So if you have to change it to like Python. Doesn't work. So quotes, human number,
Oh, my.
no quotes, human number. And so it wants to. Now,
Thank you.
yeah, so whenever you're putting the numbers in as the arguments, don't put quotes in as the
Okay.
Otherwise the computer's gonna get.
I don't see any red anymore. You got it? Oh yeah. So if you want to see just 8, you can do dot show after everything, and you can say 8 as the 1 argument. Dot show shows you the first some number of rows. Yeah, but it's got to have parentheses. It's always a function call. Yeah, so you're chaining all those thoughts together. First do the sorting, then give me the things I care about, then give me the topic. See how that's all happens together? So yeah, if you run that now, it'll only show you 8 rows. See that? Nice. Yeah. You understand the area? You're good. Nice. All right, our words are dying down. Would any brave soul like to type in the answer that they got on my computer? You want to? Yeah. Sorry about all the chords and things, but
I'm not fluent in Python on my second day.
how dare you? Yeah. It's almost
Oh.
like we're taking a class to learn something.
Is Python your favorite language?
I really do like Python a lot. It's good for quick things.
Okay.
I
Hold on. What do you have the table named as? Is it just Pokemon for you?
I just called it Pokemon.
Okay.
I like functional programming languages the best. Python does have functional features, but there are other cool languages. One thing that Python doesn't have are types. Like, and that won't make sense to you until you take CSI 40 or something. Plan on taking that.
Nope.
No.
The only coding class I'm gonna take home.
Okay then.
No offense.
No worries about it. I enjoy this stuff. But yeah, there are different languages with different flavors, and some of them try to help you out a little bit more than others. I think Python does not hold your hand as much as it could. There's a lot of things that are not errors in Python that would be errors in other languages. It's trying to make things easier on you.
Okay.
So there's a give and take there. But I think Python is a really good starting language because it kind of combines a bunch of different things that are good for learning.
Seems less evil than C++ does. Like,
Yeah,
it has
I think
less
so.
of a nefarious vibe to it.
But the thing, you coming from C++,
I'm not coming there. I'm coming there an hour earlier.
oh yeah, but knowing C++, you can do this in Python, bless you, and you can't do that in C++. And this is disgusting, right? So, good. Yeah, did anybody get anything different than this? Is this what we came up with? Because I think you could do the sorting or the where in either order, right? Doesn't matter.
Wait, how'd you make the columns only show those three columns? So I.
That's the select. Select out the columns. I only want to see these.
Okay.
See that? Yeah, question. The true means yes. So,
It makes it. I cut out the descending part, so essentially it's just saying that the biggest number is going to be.
yeah, that's shorthand for descending equals true. Usually we give the name there. That's how I taught it. Say that louder. Yeah. If you don't write descending, the default is ascending. So it would give you the weakest Pokemon in terms of defense if I ran it right now. See how the defense values are really small? So that the default is ascending. So the default is descending equals false. Descending, no. But if you want it to be, that means turns into ascending, right? But if you want it to really be descending, then you say descending equals true. Or you can just pass true by itself. But I'll teach it this way, at least in this class. Yeah, good. Those are good questions. So yeah, you can do it in either order. I think you could sort first and then do a where. And this select could happen in any order because the defense is part of the things we're sorting by. And it's part of, like, you can have the select as the very first thing, it could be in the middle, because all the pieces are still there. Like, you're not getting rid of the generation or the defense by selecting because they're included in the selection. But sometimes you have to be careful if you're only going to select out things that use other things to create it first. But yeah, the dot show 8 has to be at the end because that shows you the last 8 rows of the final resulting table. So yeah, does this all make sense to us? This is making a bunch of different tables. Pokemon by itself is a table. Pokemon.where generation 2 is a table. It's a big long one, right? Pokemon.generation 2 then sorting by defense, that's another table, right? We're chaining a bunch of tables together and whittling it down to what we want. Yeah? Nice. I think that's what I wanted to say. Any last questions about this question? So, yeah, even if we're not familiar with Pokemon, I think it's an even better example that way because you have to get up to speed on the data set your boss gives you one day. Maybe if you're not familiar with the stuff, you got to learn this stuff. So that's good.
No question, but can you change the color of the table?
The color of the table, what do you mean by that? Like this? Make it prettier? I don't think so by default. There's a way to display stuff in a pretty way, but I don't think the data science library gives you access to that. I don't think they do, but there's a way to take a table, output to a file, that would then be interpreted as you can change the markdown, maybe you can change, you can output a HTML file or something with pretty colors. That's a way to do it. But so there's always a way. I don't think it's very easy in data science land. It's totally possible. It's just be a little complicated because they don't expose that to us. But it's definitely possible. Yeah, I think that is the last thing I wanted to say before I talk about lab stuff. I do want to, is it okay? Are we ready for me to switch gears? There's just a few things that I need to show you to make sure you understand the labs. There's some things that are just kind of miscellaneous items that I want to get through to you before we talk about lab stuff. Are we ready for that? Or do you have any last questions about table stuff? You good for now? Yeah. Oh, we'll of course be here for a while if you have more questions. But I want to make a little miscellaneous section just to make sure we know all the little things that you'll see in your labs, in your homeworks. Miscellaneous. I need to spell miscellaneous. Miscellaneous things I need to teach you today. Okay. The first thing is there's a print function in Python. Maybe if you started your lab 1, then you've seen that. But you can say print, and then you can say stuff. Hi, Mom. Say it like that. And Python does not care if you use single or double quotes. I've been saying that. I just want to keep saying that for a while until it sinks in. As long as you're consistent, you can't do it like this, right? As long as you're consistent, you start and you end with the same one, then it's fine. And print forces output to appear. Print forces output to appear. And so you might be thinking, like, what's the difference between that and this? Technically, what's going on, well, first of all, this gives you back in terms of quotes, which is slightly different. But also, technically, you can think of the way that Jupyter works is you got a bunch of lines, a bunch of lines, a bunch of lines, a bunch of lines, and then you have your last line. It's always going to show you the output of the last line. You can think of Jupyter as always putting a print around the last line by default. That's a good way to think about the way it's working. But it's slightly different, but that's good enough for us. So print forces an output, which means you can say this. You can say print hi mom, and then you can say print again. Print we'll also see this in the output. And now I'm forcing 2 outputs. Does that make sense? Print forces an output. Whereas Jupyter by default just shows you the last thing in your cell. That's nice. Sometimes you have to use the double quotes. Like for this one, you had to use the double quotes because if I use single quotes, this contraction here is going to confuse Python. Be like, it thinks that the text was over after we, and then it thinks I forgot to start a new piece of text. You see that? So it got a little confused, and so double quotes will solve that. There's also a way to keep it single quotes. You type a backslash there. It's called escaping the quote, making sure that it's part of the text. So that also works, but that is a little bit harder than just doing this. Okay, so that print forces output. Print can take multiple arguments, and it prints those things out with spaces in between. So it can be like 42, 43, 44. And I'll just print them all out with one line and spaces in between. And yeah, just kind of the idea of printing is it forces output to appear. So you can be like x equals 42. Print x times 2, and then also do some more work to see some more output at the very end, like x times 7 plus 11 or something. And so in addition to having like forcing output, that was the 84, there's also the implicit output of the last line. Does that make sense to us? So if you want to see something and it's not the last thing, you can put it within a print. Okay? And I think that is all that I wanted to show you. That is all you need now to do your first 2 assignments. I think that's every piece of Python. So with that, I can now give us due dates for Lab 1 and Homework 1. All right? Just for fun, if you'd like to get ahead, I'll release the other ones. Here's the order of assignments that you'd want to do them in. But if you're not going to go watch the meteor shower tonight, here's every homework and every lab. Obviously, you don't have to get started right now, but if you want to look ahead now you can. Projects I'll release later. We aren't ready for those yet. But yeah, that's the schedule. Do Lab 1 first, then Homework 1. I think that's the right order. That's the order that they do when they do these assignments at Berkeley. And I think you have every piece of things that you need right now. And for due dates, I want to give you at least whenever I finish like the stuff you need to do an assignment, I'll give you at least a week to do the assignment. So for Homework 1 and Lab 1 first. Let's have Lab 1 be due in a week. And then maybe I'll make Homework 1 be due on the Friday. So I'll put the actual due dates in here. And remember that you'll be submitting on the class website, not on Canvas. But eventually I'll transfer that grade over from the class website onto Canvas. So yeah, this one will be due. This is lab 1, right? Yeah. So lab 1 will make due on the 19th at 5, right? Remember my due date policy. Unless you work, you tell me. So that won't be due then. And then we'll do Friday of next week. And so that's the 21st at 5. I think those are right. So that's when those will be due. All right. Lab 1 first, then homework 1. And yeah, I think I'll try to keep Wednesdays and Fridays to be our due date times. Usually it'll work out to be good there. I think that's all that I wanted to say. So yeah, you know the due dates, they're on Canvas now, and I've already introduced those things to you. So yeah, are there any last questions about anything before I let you work for the rest of the time? Because that's how I want to run the class from now on. Just like, I'll release the things, take your break whenever you want to, you can ask me questions, and yeah, just want to give you the rest of the time now to work and ask lots of questions, and I'll be here.